The field of solid-state physics is vast and old and can be called as the basis or foundation for modern quantum mechanics. Starting from the Dulong-Pettit law for the specific heat of solids and the treatment by Einstein using the harmonic oscillator equation and later corrected by Debye. This whole process was around 19 years before the Schrödinger equation. Hence, we can call as solid-state physics as the basic foundation for quantum mechanics. However, still, the question arises, what happens at the foundational level? Since we know the Bloch theorem, an electron in a periodic potential has the eigenstates of the given form. Bloch defined the eigenvectors by the Schrödinger's equation with the periodic potential on the lattice. The formulation is done by imposing the von Karman boundary conditions, and where ai are the primitive vectors and ni integers, where n is the total number of primitive cells in the crystal. Here, I have written a JavaScript program to visualize the wave function described by the Bloch theorem. The upper region shows the position space and the below region shows the momentum space. Bloch said the eigenfunctions would be of a particular form, while he completely overlooked the fact whether the eigenfunctions exist or not. The periodic eigenfunctions should be square integrable over the entire space R3, and if they are not, then we cannot interpret them as a probability. Bloch carried the calculation in the phase space for the crystal. For this, we should learn about quantum mechanics on the phase space. We will learn about finite perfect crystals and develop the classical framework. We will take the classical framework to Hilbert space and then Hilbert space to the related quantum mechanics. There are several questions that arises. Why the periodic boundary conditions are the boundary conditions? The crystal momentum is not the eigenvalue for the momentum operator. And does the eigenvectors exist or not? For this, we start from the formulation of the Bloch theorem. The Bloch theorem is defined on the eigenvectors by the Schrödinger equation with the periodic potential on the lattice. But we don't know on what phase space. Now, let's dive into some real maths. For that, you should know group theory and various Lie algebra groups. The mathematical field of representation theory, a Lie algebra representation or representation of a Lie algebra is a way of writing a Lie algebra as a set of matrices in such a way that the Lie bracket is given by the commutator. In the language of physics, one looks for a vector space together with a collection of operators on V satisfying some fixed set of commutation relations, such as the relations satisfied by the angular momentum operators. So what groups are we dealing with here? We should be using the Heisenberg group, the Galilean group, and the Poincare group. So what about their algebra? Their algebra usually consists of the commutation relation that we'll use in physics. We'll start from the phase space in a Heisenberg group. In mathematics, the Heisenberg group H, named after Werner Heisenberg, is the continuous Heisenberg group arises in the description of a one-dimensional quantum mechanical systems, especially in the context of the Stern-von Neumann theorem. In classical mechanics, we describe the state of a particle at a given time by its position q and its momentum vector p. The fundamental idea that led to the quantum mechanics was to take the component of this position momenta vector to be as operators on a Hilbert space H. They satisfy the following commutation relations. for different value of I and j. We chose the Heisenberg group for the phase shifts. They define the translation of R3 and the boost of R3. Specifically, we describe them as following. They have a specific multiplication law, and they have their own basis of generator G, which is a Lie group. The Lie algebra of the Heisenberg group over the real number is known as the Heisenberg algebra. The Heisenberg group has the special property that the exponential map is a one-to-one and onto map from the Lie algebra to the group. In the theory of Lie group, the exponential map is a map from the Lie algebra of a Lie group G to the group, which allows one to recapture the local group structure from the Lie algebra. The existence of the exponential map is one of the primary reasons that the Lie algebra are a useful tool for studying Lie groups. We do the same analysis in the dual space. In mathematics, any vector space V that has a corresponding dual vector space consists of all linear functions on V together with the vector space structure of a pointwise addition and a scalar multiplication by constants. The dual space is defined for all vector spaces, and to avoid ambiguity may also be called the algebraic dual space. We have the crystal lattice in terms of a set of linear combination of the primitive vectors. This lattice is invariant under the translation by the primitive vectors and inversions in a finite class of planes, and also by some finite rotations. So, we have only finite number of available crystal shapes. We define them by the following relations. Hence, the vector that are linear combinations of the b1, b2, b3 with its coefficient in integers form a lattice L double prime, and the lattice is called the Heisenberg lattice. This is how they describe a dot product. Next, we describe the phase space in the Galilean group. We use the Galilean group for considering the non-relativistic spinning of the electron, and we need the group representation for it. To add the spin of the electron in a theory, we must add the treatment of the rotation group. We will proceed by taking the group G defined by the Heisenberg group and the rotation group, or we can treat it by using the Galilean group. It has the following representation and the given multiplication rule. Here T is the time shift, Q is the position or configuration translation, P is a boost, and R is a rotation. The generators of the groups are tau, Q, P, and M respectively, and they form a basis for G10, where G10 is the Lie algebra. The Lie algebra commutation relations are computed to be as following, whereas the other commutators are 0. Here zeta represents the number of phase shifts. We put t equals 0 and m equals 1 and get the case considered in the Heisenberg and rotation group. This proves the claim made that the case was an orthochronous Galilean group. We usually treat the electrons in terms of the Poincare group and relativistic quantum mechanics similar to that of the non-relativistic case. Here we have shown a visualization for the phase space and how the relativistic and non-relativistic electrons behave in them. We should now consider how the momentum space, the configuration space, and the phase space differ from each other. So we should know about the momentum space versus the configuration space versus the phase space. The phase space distribution is not just the product of the usual momentum space and the usual configuration space distribution. We will show it by the use of Heisenberg group. We have a special condition in the Heisenberg group case in which the momentum space representation and configuration space are connected via the Fourier transform. Step by step, we build the kind of complicated but surprisingly small expression for the whole of Fourier transform. But just one final distinction. The final distinction is that we don't divide by the time interval. The Fourier transform is just the integral part of this. as shown here. The Fourier transform limits, we can take it from minus infinity to plus infinity, or we can take it to some specific time interval. Here it is a visual representation of same. The momentum space representation and the configuration space are connected via the Fourier transform f. Here we have shown the uncertainty principle and the Fourier transform connection. In the configuration space representations, we have the following maps. For the Hamiltonian given by h equals p square by 2m plus v, the direction of the maximum increase in q of v is plus minus del qv. This is by the method of steepest descent. As when ascend, the momentum goes down, so p equals minus constant del q. The function h will transform to h tilde, where under the Fourier transform, where h tilde is equal h of minus q comma p, where we have the following map. This is called the Born reciprocity principle. Thus we have the Hamiltonian h tilde equals minus del square p by 2m plus v. All the irreducible representation of the Heisenberg group are connected by a unitary mapping, and one of them being the Fourier transform. Assuming the eigenvalue of the Hamiltonian is epsilon n, we get the following Schrödinger equation. The eigenvectors we get are psi n. Similarly for h tilde, we get the same eigenvalues, but the eigenvectors will be different. The phase space of eigenvectors would be psi n p psi n q with the eigenvalues epsilon n p whole square. Here we see the decomposition of a normal wave to different sine waves. This is how the waves are Fourier transformed. The dot at the center represents the center of mass. We dealt with the problem of the infinite lattice by placing the above theory in terms of the lattice phase space and factoring it. This process will work for groups other than Heisenberg group. In the Heisenberg case, the theory is on a compact space and one may use the Fourier transform.